Okay, so last time we met, we had been talking about capture and avoidance techniques. And so we had just worked through this little snail example, as well as practicing our graph reading, right, which we know is one of our big outcomes for the class. So we had looked at how can we interpret some avoidance techniques or capture techniques, right? So we had been looking at these little snails and their way to avoid it, shore crabs. And so remember when we looked at A, right, we had seen that the tabula, right, had the longest handling time. And we said that had a lot to do with the concentric circles, right, the spiral shape of their cells, and the Littorina litoria, right, which has the picture right next to it, had the shortest handling time, right, so it was the easiest to get the food out of the shell if I was the predator. That has to do with the sort of the extended, right, or pulled out shape of the shell, so it's kind of easier to crunch or break. Okay. So then we talked about trade-offs, right? So if we looked at graphic B, which was predator avoidance techniques, okay, so we talked about these are like a behavioral aspect. A is morphological, a physical trait. B is behavioral. This would be something like hiding, right, or burying yourself. So we said that our Littorina, okay, had the highest predator avoidance. They were most likely or spent the most time hiding, where our Jabula, right, spent the least. Okay, so this was that trade-off, right? So our take-home, right, and right at the end of class was talking about you don't want to spend all your energy on this sort of business, right? Because then you're not spending any energy on anything else. I'm never feeding, okay? I'm never breeding, or producing offspring, so I don't have any of that biological immortality, okay? So we want to balance how much time I want to spend on this. I want to spend some, right? Because this is ultimately not death, or my ability to survive. But so there's going to be no perfect technique. So I'm either going to spend energy on having a good strong shell, or I'm going to spend energy on hiding or being cautious. But I don't want to spend energy on both because that's just too much energy. Okay, then I'm just diverting too much from all these other things I also need to be doing. Okay, so that's where we left off on class. Any questions about that before we move on? When I do that, it's not like. Okay, let's take a look at this graph. Okay, take a hot second to explore the axes and the data represented here. Alright, what's going on this bad boy? What's my y-axis? Number of fruits, right? So what kind of organism am I talking about? Some kind of plant. Okay. So my plant is producing fruit. Trying to balance an animal on a plant example, right? Okay, so what's going on in my x-axis? Okay, so I'm clipping fruits or I'm clipping tissue, right? Okay, so I'm clipping tissue on these plants, and then I'm looking to see if there's a response, or how many fruits or how much tissue is coming back after that clipping. What's the term for that? Compensation is correct. So they're early today. Good, so compensation, right? The term of when tissue becomes damaged or removed from a plant, right? And so they grow extra or grow more to compensate or to correct for that loss, right? And almost in anticipation of that continual loss. Okay, so let's take our dates in pieces here, right? Because there's a lot of information in this graphic. What would our control be? No clippings, right? Okay, so we want to compare all of this business to a plant we have not damaged the tissue of. So how would this plant normally grow unfettered? Okay, so the other three bars here are all of plants that have been clipped, correct? Okay, so now we're just looking at how far into the growing season have we clipped the plant. Okay, so do we have compensation happening? Yes, right? So if I compare any of these clipped plants to my control, okay, some of these clipped plants have significantly more leaf tissue, right, and fruit in this case, right? So here's my control with its error bar. Okay, at around, let's just round up for the sake of argument here, 15 fruits. Okay, in particular, July 12th and July 20th, okay, both have significantly more, right? Even with their error bars, okay, they are much higher in fruit count than the control. Y'all see that? Remember, when we read these, we want to see differences between our error bars. Because what's an error bar? What's an error bar showing us on these? What's the bar part showing me? The error bar is my deviation, right? So what's the bar? An average. Okay, so the bar is my average. So on average, plants that were clipped July 12th had 28 fruit. Right? Okay, now, did all plants have exactly 28 fruit? Assuredly not, right? That would be crazy. Awesome, but crazy. Okay, so the error bar is giving us an idea of like, well, what is the variance around that average? Okay. So we may have more or less, I don't know, what does that go up to, like 33-ish? Okay, so plus or minus 5. So that's what we mean by standard deviation. Okay, the variance around the mean, and particularly when we're looking at bar graphs, right? I'm kind of guessing because none of these are falling right on the lines for us, but that's fine. Okay, so this is why it's important when we look at these that we want to make sure if we say, well, there's a clear difference, we include those error bars, right? So the best graph that's going to show the biggest differences are going to have the smallest error bars and the error bars that are the furthest apart. If I have really, really big error bars, what does that mean? Right? If I had error bars that looked like this, sorry, buddy, what would that mean? Even if my bars were, or my actual bars were real small, what would these error bars mean? I might have some outliers. Right, so that maybe, right, there's just a lot of variation around that mean. I might have, I don't know, 5, an average of 5 fruit per plant. Okay, but to get an error bar like that, I'm going to have some that have 0, right, and some that have like, I don't know, 30, 20, right? This is all over the place. Okay. When you have really, really big error bars, that means that whatever it is you sampled had a huge amount of like variance, right? So an average is only telling you so much. Right? If I sampled our average age in this room, okay, the average is going to be close to what, 21-ish? Okay, but our error bar is a little big. Okay, some of us are somewhat older. So we have to have the variance to reflect. There's more variability than the average is going to reflect in that, right? That makes sense? Okay. Let's get rid of that black bar so we can explore what's going on here a little bit better. Okay, any questions about any of the stuff we just talked about? Okay, so we see that in particular, right, July 12th and July 20th are showing compensation. Right, they have significantly higher number of fruits when compared to our control. That make sense to everybody? Oh, that's the eraser. Okay, what is going on with July 28th? It was clipped just like everybody else. Is that showing compensation? No, right? Why? Too late in the growing season. Right, so we've hit some kind of threshold here, and we can see a trend. But we're going to invest less and less fruits, right? So eventually we've gotten to a point where, despite the fact we've been clipped, and this plant clearly shows compensation, you're eventually going to get so late in the season where it's not worth investing energy in fruits anymore. Because the likelihood that those fruits are going to be able to drop their seeds in the soil, and those seeds are going to be able to take hold and survive before the fall frost is not as good. Okay? So I want to put, as a plant, my energy investment in other parts of my body. Right? Leafing, photosynthesis, right? Structures that will help me survive the winter. Okay? As opposed to my theoretical babies that will probably die anyway at this point. Right? So it doesn't make sense this far out in July to invest in reproduction anyway. But I don't care that you clicked on. All right, great job. That makes sense? How we worked through that? Okay, so there's a lot of information here. It also gave us the opportunity to work through, again, what bar graphs and error bars mean. Okay. And this is what we just talked about. Okay, so our first statement here, and I have the plant, right, the gentians. But the idea is, right, if we do it early enough in the growing season, we see compensation. We don't later in the season, right? And that may be because they clip too much, but that's unlikely. It's more likely there's not enough resources or it's not worth it later in the season. And it's still true, though, for any plant, right? Just like before, we're still going to have a balance. So you will not compensate if you cut 90% of the tissues away, right? Okay, so if you remove too much tissue, and we still don't want to invest all that energy into trying to replace and overgrow that back, right? You will eventually hit a point where now I'm just trying to survive. And so most of the time when we're talking about compensation, right, we clipped a little bit of fruit. Okay, the caterpillar has come through and eaten a handful of leaves. So I would come back and do lots of growth beyond that. Okay. If we think about too much tissue, we could think about massive damage loss, right? Huge branches being ripped off, right? Large portions, greater than 60 or 70% of the plant being damaged. Okay? When you're talking about great loss like that, okay? Sort of like being in triage. You're not going to see compensation come back from that. You're really just going to see the plant try to not die from that. It's all going to be about repair and regrowth for that season. What can I do to try to keep myself from dying? What can I do to get back into standard photosynthesis? So there's a limit to all of these things, a balance to all of these things. All right, any questions about that example? You guys are going to be pros at graphs in no time. Okay, anything about anything we've talked about up to this stage as we kind of flip topics here? Okay, so we mentioned a little bit previously when we talked about diet that some predators are preferential. Okay? And when you see more preferential organisms, their population sizes, so if we think back to abundance, become closely linked. And so one of the ways we have tracked this in the past is called the Lodka-volterra model. Like two Swedish people. Just get stuff named after you when you discover it. And so what they generally suggest is that all predator and prey populations cycle we can already think intuitively that maybe they got a little excited. Okay. But we do see this to some degree everywhere. And it's more obvious in predator-preys that have this really strong preferential link. Okay, picky eater syndrome, if you will. In other words, okay, if I'm really kind of picky about the things that I eat, okay, as their population goes down, my population will go down, right? I'm more or less dependent on how much food I have to eat. As their population goes up, okay, there's a glut or a feast of food, my population can go up because there's a lot of food to eat. I can feed my family. I can have more in my family. Okay, so we see a linking of some of these populations together. And to some degree, it's always like that. Okay, but the pickier the predator, the more strongly that link is. Okay, so let's look at an example set of how this works. And one we've already kind of teased with. So if we think about population cycling, as I mentioned, and what this first bullet point sort of argues, it's not super common. Right, because as we've already talked about when we talked about predator and prey abundances or population abundances, there are a lot of moving parts, right? In the lab, what incidentally tends to occur is predators eat that prey to extinction and then everybody dies. Horrific death. Here's what it doesn't tend to happen in the wild. If we think about these two pieces that we talked about already. Okay. When predators are hunting, the success of being able to find things, we already talked about things like handling time. But in addition to those two things, we have search time. Okay, so how much time does it take to find what I want to eat? Okay, so we can imagine this is based on how many are there? Just ease in me, or just not great on these screens. Okay, as well as any predator avoidance. So if they're hiding, if they're shy, okay, if they're being conservative, right? So they're not going to let you get very close. Okay. Search image is the other piece. So how good am I at recognizing my prey item? And this might mean quite literally, I see rabbit, recognize rabbit as food. This may also be pieces of my food. I recognize rabbit print. I recognize the urine trail of that rabbit and can follow it. All of these pieces collectively create the search image. My ability to actually find that food and put it together in my brain as dinner. The fact that these things are hard in the wild, easy in the lab, right? Because the prey doesn't actually have anywhere to go. It means that you're very unlikely to drive your prey item, your food item, to extinction, because they will eventually become so low in abundance, so shy, right? They'll create very high predator avoidance techniques. Okay, so at the very least, this item will become very difficult. Okay, that the predators will have too much hard of a time finding this food item. So let's look at the graphic that we have up here. And what we see, right, is that we have sort of an offset oscillating, meaning you get that like wave pattern, curve set. So if I'm focused on the red line, that's my prey. Okay, I see here that my number of prey, right, my population abundance is increasing. Okay, now this is happening for several reasons. The first of which is because we're starting out with a low number of predators. So there aren't a lot of predators to be hunting me, right? Nobody's in the trophic level above me to eat me. It starts. So this gives me a chance to sort of run around freely. I don't have to be as conservative. I can spend more time hunting my own prey, in this case kale, I guess, as appropriate. I can invest more energy in breeding, living my best rabbit life, right? So as I'm doing those things, my population will continue to increase. That make sense? Now, here's the stick. As the prey population increases, right, they're out there living their best life, having sweet little rabbit babies, having little rabbit parties out in the forest. Okay, their population is increasing, right? So the search time for finding rabbit food is going down, right? There's more of them, so they're easier to find. As the search time goes down, they're easier to find. Our predator population can turn the corner and slowly start to increase as well. Okay, so this is in response to there being more prey, right? And that search time going down, more food being easier to find. So this is why we see this offset, right? Because we had to have had food for the predators first, for the predators to have been able to eat that food, to see the food. And now there's a natural repercussion to this then, right? As the predators are able to more easily find a bunny rabbit, okay, that's going to start to have a negative impact on the bunny rabbits. Right? We can't go on eating them forever and not have a negative effect on their population size. So as we get more and more wolves, right, that are able to have more and more babies because rabbits were easier and easier to find, eventually all of these wolves and their wolf babies start to negatively impact the rabbit population. And so as we hunt the rabbits more and more and more, we start to reduce their abundance because there are just so many dag-nabbit wolves. Still with me? But again, okay, now that we've eaten down the rabbit population, okay, we've increased that search time again, right? Because now we have very few rabbits. So now that we've increased our search time, hunting rabbits begins to get harder and harder and harder. Food becomes harder and harder to find. And this will slowly start to reduce our wolf population. So on and so forth, till the cycle starts all over again. Okay, so when we're talking about population cycles, this is really what we're talking about, right? We have this little bit of lag. The rabbits go up because there aren't many wolves. Okay? After we get enough rabbits, it's easier to find rabbits. The wolves can start to go up. Okay? Once the wolves start to go up, it kills off our rabbits. And because the rabbits are low, they're hard to find again, so then the wolves start to die because there aren't enough foods. And we start to see that lagged, oscillating cycle fashion. I don't think wolves are that picky, but you get the idea of what we're going through here. Does this make sense? Okay, what Lodka and Volterra were proposing? It works better for some organisms than it does others. Now, we know that population cycles are not only affected by predators and prey. Okay, first off, it's rarely just one predator and one prey. Okay? So we talk about how a handful of predators are really picky, and I will give you an example of where this is a real thing. But we don't want to get too caught up in it. Okay, so for example, we talk about things like wolves, they tend to eat more than one thing. So if the rabbits were to die off, remember that they usually just prey switch. Okay, switch to a prey that's more abundant. Okay, this still gives the rabbits a chance to bounce back, and it would just reduce the abundance of a different prey. We also want to keep in mind that multiple trophic levels are usually in play here. Right, so our predator may have a predator, our predator may have competition, our prey has their prey. All of these things matter. Oftentimes, the prey have what we call spatial refugia. In other words, spaces that the prey can go into that the predators just can't get. Okay, this may be burrows, thickets, getting up in trees. Okay, whatever the case is, if the prey is small, they just get somewhere that the predators can't get, somewhere spiny that the predators can't get. Maybe the predator can't climb. Okay, spaces that they inhabit where their predator cannot be for a significant proportion of their lives. They obviously can't spend 100% of their time here, but it's going to significantly impact, okay, that search time or search image impact, right? Okay, so we're acting like, okay, search image is just based on the cognitive abilities of the predator, and search time, right, is just based on things like abundance. But it's certainly far more complicated than that, and things like habitat complexity and habitat connectivity are also really strongly important here. Any questions about this, right? We want to keep this in the back of our mind. You know, this isn't to say that lotka-volterra isn't important. I wouldn't bother talking about it otherwise. Okay, but it's not nearly as important as it's kind of sold as. Okay, any questions about how any of that worked? Okay. So a really good example of one that this actually works at is if you remember in the diet option, we talked about the links and the hair. This is really, I think your book does this version if you happen to have the book. Oh, we all have the book now, it's free. So the links and the hair is a really classic example, and it actually fits almost perfectly because the lynx is a super picky eater. Right, it's like a 5-year-old child. So the lynx pretty much only eats snowshoe hair in particular, so like super picky. Okay, like my brother when he was 5, and he would only eat frozen cheeseburgers and he would deconstruct them. I am also not kidding. So when you see those two patterns together, even though, of course, okay, we still had multiple levels, the hare ate things. Not a lot of things eat a lynx, right? It's a moderately sized cat. In sort of like a tundra-like area, there aren't a lot of other predators that are larger than it. Not a lot of other predators exist in the area that can tackle a snowshoe hare. They're small and quick. So you need to really have that capacity, right? Really the only other thing that eat it are like snowy owls. Okay? Not direct competition on a lynx, right? So that's a really tight lotka-volterra. You can also imagine as you start picturing this scenario, kind of how rare that sort of setup is. And so it is in fact more common in areas that are boreal or tundra-like, where you're going to have limited competition. All right, any questions about our population cycling? That's a kind of a bigger topic, more complicated. Okay, let's go ahead and stop there today. Whatever we get through on Wednesday will be the last set of topics for your test.